Yeah, thank you all. Thank you all for having me. Yeah, it definitely reminds me of a CAP 414. But yeah, so today, so sort of the outline for this presentation is going to be starting off with the motivation for this work, followed by sort of some setup and notation, and then we'll get into it. But sort of this additive inflation property we're going to talk about, and then sort of a slightly stronger idea of multiplicative inflation. And then we're going to get into like basically sort of some data splitting type techniques, followed by some empirical results. And I have a sketch of one of like some of the more an interesting trick that we use in this work. So yeah, so the first thing that people have seen a lot about is like linear regression. Um, and sort of the idea in this paper or this work is to talk about what happens when our basically our number of parameters really exceeds our number of data points. Um, so like classically, when we talk about like number of data points, like we're going to call it n, and then the dimensionality is going to be d. So when basically the number of data points is less than or is more than the parameters, it's a pretty well known problem. And in fact, basically the idea is there's these shrinkage type methods that we can use, like James Stein, to basically move our estimator, like our least squares estimator, sort of closer to zero or some other point to improve like the test error, the generalization error. And then more recently, sort of people looked into this case where we say, okay, well, n is actually less than d. N and d are proportional as you take sort of to infinity. And so in this case, a lot of people have studied some of these isotropic regimes where they found that basically positive ridge regression, or sort of, again, ridge regression is another type of shrinkage method, will basically improve your test error. And so the basic idea is that when you're near isotropic or near, or or near isotropic, when you see a new sample, when n and d are sort of proportional, that can reflect something new. But when you have so many more dimensions than samples, it's basically you're just going to see something that's orthogonal to what you've seen before, and so it's not really clear what you can learn in that regime. And so the idea here is to look at when we're anisotropic, what do you get out of that? And so that's sort of the idea here. Next slide. So we're going to consider the setup where we have n IID samples, basically all Gaussian with some positive definite covariance matrix. And then we have some assumptions on our noise. And basically the idea here is, we want it to basically be bounded conditionally on our expectation or on our basic data or covariates and mean zero is sort of the big idea. And then we're still looking at linear regression. I think one thing to note here is just that everything can be thought of as a function of n. So we're taking n to infinity, and everything else is sort of like a function of it. So that, for example, the covariance matrix changes as you take n large, and so can the distribution of the noise and such like that. And so we start out, we basically X be the design matrix, and we're going to take basically this, it's called the minimum least squares interpolator, is theta mn. And it's essentially it's the over parameterized analogous of least squares regression. And so basically without noise, it sort of just is the projection of your unknown vector onto the space that you've seen. And with noise, it's a little more complicated. And then basically we're going to R of theta be the risk. So basically what is your expected error on a new draw of the data? And then G is going to be what is basically the generalization. So basically the expectation over all the draws of the data, what you see. And so this C opt is basically we're going to talk about in the terms of inflation, which is like basically what is this when you scale theta mn, like what is the optimal scaling? And what we're going to try to look at is when is C opt greater than 1. And so before we get to that, I just want to discuss negative ridge regression for a second. And so negative ridge regression, you typically, is sort of a newer idea. It's been around for a while, but at least its use in practice was sort of inspired by this paper, Kobeck et al. And they sort of looked at actually in real world data sets, you can actually want your optimal ridge regression parameter to be negative. But the question, of course, is what does that mean? So the typical definition for the ridge estimator when lambda is positive is basically doesn't really work because if you were to take a portion of your theta to be perpendicular to the data, you could basically scale the problem down to negative infinity, essentially. So instead, they just sort of take the solution to the original minimization problem that's posed by ridge regression and just allow lambda to be negative. And one of the motivations for why this might work or why this might make sense is that suppose that we sort of have a covariance matrix where we have a ton more parameters than our data set, and we sort of all these excess sort of independent noise parameters. And so what happens is when you take that those excess noise parameters to be very, very large, you essentially end up with a regularization factor that's almost identical to what you see in ridge regression. And so in this case, if you imagine that you're already overly regularized, then it might make sense to actually put some negative ridge penalty to sort of bring you back to this optimal ridge regression. So that's sort of one of the motivations for like why you could think of negative ridges making sense. So what were kind of the cases in that Kobeck et al. Sort of found as to be like when this occurs? Well, one, we need it to be anisotropic, right? If this is all just an identity, it wouldn't really work out. We also need sort of beta to be well aligned with the top eigenspace of sigma. In this case, we just sort of have this, we did sort of as a pedantic example, very well aligned. And then also for more general cases like a spiked covariance matrix and such, they found that like D or dimensions needs to be at least like super linear than N. Like it can't just grow linearly or proportionally with N. And so based the idea like the inflation property or kind of the additive inflation property is when can you just get it all that you want to scale away from zero, or like kind of the idea is like shrinkage infinity, like you're shrinking instead of shrinking towards zero, you're shrinking away from zero, which is like kind of infinity on the line. And
Jake,
to like
go back for a second, show the definition of G again.
It's the expectation over all the draws of the risk.
Okay.
So this is sort of the diagram that shows how like this thinner line here is the ridge regression, sort of how it looks negative and positive parameterized, and then obviously inflation sort of just on this line. And this is kind of how it affects the eigendirections. So inflation sort of equal for all the eigendirections, and the ridge sort of acts much more strong in the bottom part of the smaller directions when it's negative, and obviously the larger directions when it's positive. And so the inflation property sort of occurs when you have like similar ideas to what you talked about, where essentially we have basically assumption one, just a normalization that we're going to use just to make everything sort of order one in the outputs and sort of make the covariance matrix all similar. And essentially what we need with this lambda one condition is that the effective rank of the matrix is not too crazy. Like we still need it to be like either on the order of n or like n squared. We still need to be fairly large, but the effective rank still can't be too crazy. And the second one is basically an assumption that just comes from our assumptions on the noise. It's mostly a technical requirement, but it's not particularly imposing. And then this last assumption is sort of the more important assumption, and we're getting into kind of what it means. So one thing is you can look at like this last part here as like the inverse of an effective rank. So like one of the measures of an effective rank, and sort of it's imposing an inverse. But an equally better and perhaps easier explanation is that suppose your beta was just some random isotropic vector. Essentially, this is imposing a condition that we want beta to be better aligned with sigma squared than it is aligned with a random, than sigma squared be aligned with a random isotropic vector with some adjustment for the noise. And so based on those conditions, we have the inflation of property occurring with, but the issue here is that it could just basically vanish as you take n to infinity. So we want something slightly better than that. We don't want to necessarily have it just vanishing in our limit. And one of the, you can think of this kind of additive is like if we were taking everything towards zero, if the scaling was such that, our generalization error or test error was kind of shrinking to zero, this would be like a higher order additive term that's sort of helping, but not too crazy. So the question is like, when can we get better than that? And so that's what this idea of like multiplicative inflation properties. Can we change and get like a bound on the generalization error that doesn't disappear when we go to infinity? And so we'll get into the assumptions in a second, but basically the idea is that when Q is small, which is basically, we'll get into exactly what that is, but essentially it's when we're sufficiently a high effective rank, but nothing too crazy, again, we can end up with this result, and we're going to talk about the assumptions. So first, before we do that, let's talk about kind of some of the spectrums that can be solved here. So we have a block diagonal matrix. So that's kind of similar to the negative ridge example. And then another one that we can handle is sort of the power law decay. And the alpha here is just basically chosen to keep our condition of basically the trace being equal to D. And then we can also handle like multi-block power laws. So this is a 2-block power law decay. And again, the assumptions that restrict which ones you can use just come from our summability requirements. We can also handle for appropriately scaled spiked covariance matrices. So just like a rank 1 update to the general covariance matrix. So before we get to back to the exact ones we talked about earlier, a simpler set of assumptions is basically we have this set of growing and well separated eigenvectors that essentially the rank and the beta is well projected onto those. And we also require that basically that's kind of like the main way to think about like this, and sort of coming back to like basically the last assumption that's sort of hard to understand is sort of these in the original one is what does Q mean? And you can think of Q, and you can really think of any power or anything of this form as a moment of a appropriately constructed random variable. So in this case, because of basically the beta transpose sigma, beta is 1, we end up where essentially we can create these into essentially like a expectation, because we already have the summability on, or summation to 1 on the 0th moment. And so with that in mind, we can see that essentially we are imposing a condition on how fast the second moment in this sense grows compared to the mean or the first moment.
What is the lambda? You said lambda is a random variable.
Yeah, lambda is basically like it's a random variable that has like the following probabilities.
Okay.
Where vi is like the ith eigenvector. If that makes sense.
Yeah.
So with that in mind, so I was saying there's like, we can basically get this Q as like the mean in the sense of sort of this covariance beta alignment. And we're basically saying that we can't have the second moment dominate the mean too much, or the mean squared too much. And then we're also saying that we don't want we need like some sort of like the isotropic like variable part. Like we don't want that part to be too close to the mean as well. So this is sort of enforcing some anisotropicity comparatively. And so when we have these assumptions, we can essentially find this alpha that's strictly less than 1, where our optimally scaled theta min or theta mn beats this other scale, the scaling on the generalization error itself of just the regular theta mn. And obviously this does not vanish in the limit. And this, you can kind of think this is changing the scale of like a rate. So some interpretations here One is that potentially because of the anisotropicity, uh, theta mn is sort of overly aligned with sigma cubed compared to where it should be, and that essentially the scaling kind of removes that dependence. In a similar sense, we can kind of see that maybe the lengths are contracted, where the anisotropicity basically creates some differences in the geometry compared to like a Euclidean geometry. And basically, we're increasing the length of the vector to account for some of the loss in the tail because of that anisotricity. And then a third and more interesting one, it relates to the Johnson-Lindenstrauss lemma, which basically states that a random Gaussian projection matrix with isotropic covariance, basically all the entries generated from like normal 0, 1s, is approximately an isometry. And here, when we remove the noise, we sort of have a Gaussian projection matrix that's anisotropic. And so the question, basic idea here is that maybe the scaling helps bring you back up to where you need to be in isometry. And that's sort of why it works out for the theta mn to improve the generalization error.
So how does this estimator, after you shrink it, compare it with the optimal reach regression estimator with negative reach?
Yeah, so in the empirical part, I can show you where we compare the two. It's a little hard to do the negative ridge theoretically because you end up with a lot of issues around where the ridge parameter can cause a lot of spikes. But I do show it with empirics.
But if you under this set of condition, can you prove X transpose X has a positive least singular value that allows you to take negative ridge?
Yes, it would have a positive singular value, but it wouldn't be the optimal ridge would require you to like have some adaptive technique because you'd actually want to here. Let me just pull up one of the examples where we do it here. So like this is on a data set. We'll get into this in a second, but basically the optimal ridge regressions like here, but where a lot of the lowest singular values might be is like here-ish. So you have to like have an adaptive thing where if the smallest singular value of x transpose x is not smaller than your ridge, you have to basically either have no ridge or something like that, and then you have to have a higher negative ridge penalty when it is sufficiently small or large. So it's from a theoretical perspective, but as you can see in this one, for example, it does about 25% better than the negative ridge estimation. Is that sort of good for now, or?
Yeah, good.
Awesome. And so some of the other questions are like that can kind of come up is, is it just a debiasing, right? Are we effectively just making our theta mn just slightly less biased with our beta? And the answer is no. Basically, if you try to debias or make theta mn like unbiased, you end up with like pretty divergent generalization error with some very mild assumptions that nothing shrinks too crazy. And I think for the most part, these would hold for most data sets. And the other question would be well, can we just shrink to another point? Is just moving along the line sufficient? And the answer is likewise no, because we can basically always construct sort of a beta and a sigma that basically blows up your generalization error if you allow shrinking to any other arbitrary point. And basically, we just require like among the set of things that satisfy the assumptions for the additive or multiplicative improvement. So those are sort of the parts that you can't do. And so sort of the next questions are, to what extent do we get some concentration? Like obviously we're looking at the generalization error, but like the risk matters too. Like and can we estimate C-opt And can you obtain a better than just a multiplicative improvement? Like, could you obtain something that's shrinking to zero while your generalization error is order one with just the non-scaled estimator? And so to do this, what we basically really need is like this data splitting type technique. So basically the data splitting is somewhat simple in the sense that we have some number of splits and we basically partition the data evenly among those splits. And then we end up with sort of some excess at the end, which we will use. And that's sort of the last partition is the one with the excess number. And so then we basically like our yi is just sort of the corresponding elements, and we could basically construct a minimum norm interpolator for each of our split datas. And then we basically add them up all together. And we'll get into why we don't average over them in just a second. And then we basically, instead of having C opt, we're going to find the C star, and we'll explain and look at how close they are, and they're pretty close. Alrighty. So essentially, we have, and we'll show this, is that because you're so high dimensional, you really need every direction you see. And so each of these splits is already scaled by how many splits we have, essentially. So they're already an implicit average. And one of the interesting things is that by doing this, like we end up with like we're more anti-regularized in each split of the data. Like we're in theory should need shrinkage, but we're also averaging, which is a regularization technique. So it sort of evens out is the way you can think of it. And so here we're talking about basically how close the two are. So essentially they're both in the order of like 1 over rho, which is sort of the leading eigenvalue of the covariance matrix. And so we have essentially a fairly minor thing when rho is small, which we kind of assume we don't take rho small, but we take q, and they're actually also order of q. So it doesn't really matter that much, and we're not looking at anything too large here. So was there a question, or did I just that?
No, I don't think so.
Awesome.
Just background noise.
No worries. All right. And so the next part of this is sort of, well, how does our generalization error on our data splitting relate to our generalization error on our minimum norm or our regular non-data split predictor? And the answer is like, it's pretty good. We can think of like being order 1 minus something, or I guess in this case, eta would be like our alpha in the multiplicative case. And we're talking about something that we're taking to be sufficiently small. Like if you recall, like we take q to be sufficiently small in the multiplicative inflation property scenario. And so ultimately it doesn't actually change anything too much. It's like a lower order effect that we end up with. And so from there, what we can also see is that with this in mind, we can in fact actually obtain like almost like a rate improvement in that sense, where our generalization error is order 1, but our actually optimally scaled generalization error with this data splitting estimator is little o of 1. And essentially, the big difference here is that we need the so-called mean of this lambda variable, or this basically the variance, to be little o of 1. So we need the mean in the second moment to be, or the mean squared in the second moment to be sort of on the same page. And then we also require this condition here be little o of 1. So what this basically means is that we need the effective rank of the covariance matrix to be like n log n, or n up to n squared. So basically it needs to be somewhere between n log n and n squared. And one thing I forgot to comment on earlier was that with these conditions, like we can generally handle like up to like a signal to noise ratio of like 1 over n. Like basically the sigma squared can be order n, and obviously the average size of our signal is order 1 from our assumption here. And that holds across all the properties that we've discussed. And so one thing to comment here is that in some cases, it may be possible to get this to show this result for the minimum norm, just the regular minimum norm interpolator, but it is significantly less tractable and such. And so then here's basically a quick example of one that obtains it. Like essentially, go back to the block diagonal example, and as long as the signal at on the bottom part of the spectrum is sort of comparable to the signal on the top, we would get it would satisfy these assumptions. Obviously, there's a lot more examples that would satisfy it, but that was a pretty simple one. So in other words, this also shows you is that the fact that lambda has low variance is not indicative that it's not lambda does not reflect a covariance matrix that's very well anisotropic. And so now let's sort of think about estimating our C star. So basically we have this leftover portion of the data, which has basically this roughly half the data that the rest of the samples have. And so we're going to relabel that, and we're going to construct this estimator like this. So we're going to use the data that we know, and then we're going to contract it with sort of these independent sets of data. So this is like sort of emulating our outputs here. And the idea is that basically the numerator and denominator are going to be unbiased for the actual numerator and denominator of C star. And then asymptotically, this entire thing will be unbiased for the expectation for C star. So now we have basically a proposition for sort of the concentration around a C star theta ds, sort of how well does this estimator do? So the first thing to note is that we need to figure out we're basically saying in this proposition that we're going to tell you the optimal number of splits. And that's because we need to balance some things. Basically, the splits are used to balance how the variances of a few different objects. For example, obviously, this all depends on how many data points are in n over n, but also for some of the things, we need to make sure that the variance of all the different sort of theta mn on a subsample also does converge when it sums out. So roughly, it's going to be square root n. It's like n or so, and it does depend a little bit on what sigma you give. And then we also can have a sort of a delta, this thing just vanishing, just to show that it's a little bit better than just a fixed concentration and probability. And so the first thing is we have that we do in fact concentrate, in probability around C star, and also this does occur in expectation. The next thing is also important is that the risk also converges in probability around its mean or so. So those are both great. We did look into like how to do this for when we were in that super multiplicative case that we found, and it doesn't seem particularly tractable. Just the techniques don't yield sufficiently tight bounds on some of the objects to guarantee that. And then like as in like we can't get the ratio of these to converge in probability. And then if you recall, we had this alpha in our multiplicative inflation property theorem, which was sort of how well we could shrink our original generalization error. And we actually do obtain that in the limit. Essentially in the limit, like in probability, we on average in probability will always beat the naive minimum norm interpolator estimate. And so the next thing that we consider is in Kobach et al., one of the methods they looked at was this Fourier feature setup on the MNITS data set, which is just basically a bunch of images of digits. And so there's about 784 pixels on them. And basically what they did and what we did is multiply by a weight matrix to get the features. So basically, the real and imaginary components are basically combined, and that's sort of the features were, and then just doing linear regression to on basically classifying the digit. Nothing fancy on the linear regression. Basically, just the mean squared error between what you know the digit is and what your estimator is for it. And so here we see basically the comparison between ridge regression, the inflation, and basically it's the optimal one. And this is about as high as you can before it blows up for the ridge. And they do stop, I think, at negative 80 is where they stopped. But basically, the inflation, both of them beat just the standard minimum norm interpolator. So some sort of shrinkage method does worse. And it's about like it's a relatively minor improvement on both of them, but there is an improvement. And also the inflation property does beat the negative ridge. And one of the nice things is that basically probably one or across all the test sets that were used in this, the inflation property was always more beneficial than not inflating. And I think that was the same thing for the negative ridge regression. And so this focuses on some genomics data. So this was not in the Kobeck paper, but in this one we looked at sort of protein concentrations and of certain like genome transcriptions in some cancer patients, or some data from that. And this is sort of like the ideal data set to look at these things, because there's really a large number of genes in the genome that are not necessarily very active or sort of not turned on. And your concentration is very much aligned with the active genes. So you have a lot of this sort of low, basically low variance covariates combined with these sort of high signal covariates. And also you have very little data. Like you have a lot of these data sets, especially in these cancer studies, are going to be like 50, 100, 200 patients. And you have like 10,000 or 5,000 features. So it's sort of an ideal one for this case. And in this scenario, we have that basically the inflation property ended up beating the naive, just do the linear, basically the high dimensional least squares by about 40%, and it did about 25% better than the optimal negative ridge parameterization. And those are both statistically significant. There wasn't a huge amount of test data for this, but that was the case. And this is the data from Kolaski et al. 2023. That was actually a Nature Journal article. And so the next one we want to talk about is sort of these non-Gaussian distributions. So in this case, we mirror the setup that sort of the toy example that Kobeck et al. Provided in their paper. I sort of put the parameterization down here. And we did it across 3 different distributions: the Gaussian, which is in blue, the Laplace, which is in green, and the chi-squared, which is in orange. And all these distributions were normalized to be mean zero, basically variance one. But I mean, obviously, for the individual covariates, we imposed the covariance matrix on them. And basically, one of the interesting things here is that the more helpful inflation was, so for the Laplace, it was significantly more helpful for inflation than compared to ridge or the chi-squared. The more helpful the inflation was, the better or the worse it performed in the negative ridge scenario. And that could be an example of basically negative ridge really acts on emphasizing the bottom portion of the spectrum, or the empirical covariance spectrum, whereas inflation sort of scaled everything equally. So it could be getting at, slightly different effects there. And then that's sort of basically the exact order that occurred. And yeah. So we're now going to move to sort of like a proof sketch of what I thought was a very interesting property that sort of wasn't well known, or is not well known in the literature. So like projection matrices or expectation of projection matrices are pretty well known when things are isotropic Gaussians, but when they're in this anisotropic case, like the same techniques don't work. So you have to change that a bit. So the goal here is just to show, hey, basically it's approximately a scaled version of your covariance matrix, which makes sense. If you take the trace of both sides, you get basically n. So that's good. And we're basically going to take Q to be sufficiently small. So that's also great. So essentially, if you look at the off, if we think about sigma as diagonalized in a basis, if we look at the off diagonal entries, they're going to be mean zero here. This is just basically we're decomposing our covariant or our projection matrix. And so we can rewrite it like this with this A matrix, and this A matrix we're going to talk about because it's very important. It's kind of what comes up a lot here. And so we can really just focus on the diagonal case. And the standard technique here is just to use Sherman-Morrison to just basically separate the A, in this case we call it AI, from the particular vector that you're looking at. But we still need to figure out what are these inverses of these matrices, like what are the expectations of their traces is essentially the key question that we need to figure out. And to do that, we're going to look at sort of like this theorem or this proposition that's sort of informal here. And we basically have this recursive relationship for higher moments. So we're not we only need for this particular example that we're looking at or this particular sketch that we're doing just a second, but you can in principle go arbitrarily high. You just need slightly more regularity on the top eigenvalue. And that's sort of where this condition that we had originally comes from.
So what is your A? Sum of lambda I with Gaussian AI transpose?
Yeah.
So lambda I is from the empirical covariance or the true covariance?
The true covariance. So you need to have some assumption on the true covariance, but yeah. So yeah, so like the key idea here is that we're going to use Stein's lemma, and we'll get to in a second, but we're going to define a sort of arbitrary object and take its derivatives, and we end up recovering the trace that we're looking for. So this is kind of what we want to get in the end anyways. We need to figure out how to handle the rest of this stuff, which is you can kind of see is going to be a little lower order. So just to refresh everyone on Stein's lemma, it's basically Gaussian integration by parts. So essentially you have some regularity conditions that aren't going to be that big a deal, but essentially you can take, this A transpose object and you can rewrite it into a nice form of just its derivatives of this F matrix. And we're going to use that here. And this is quite a bit of work here, but we're going to try to work through it. So essentially, if you come back and you think about, well, what is this trace here? Well, it's really just the sum of a bunch of these for different i's. And that's sort of how you get to this part over here. So that's how you get the lower portion. And you kind of see this here, right? And basically apply Stein's lemma here. And this from part is just basically going to be the trace of our covariance matrix, which is D, times sort of what we're trying to solve for. And then we get to like these lower order objects, which are higher order objects that we need to handle. And essentially, we can just reuse the fact that we can use our bounds on our matrix here, like very naively, to basically simplify the problem. And then we end up, if we bring this lambda I in, like this will simplify down to a trace. It's lower order. And this will simplify down to a trace. And then from here, we can essentially recover that this trace is basically upper bounded here. So that's sort of like the trick with Stein's lemma that we use here. And then the lower bound, basically, if we come back and we recall over here, like we just take this portion of the equation, and we note that this is going to be, a positive quantity. Everything here is going to be positive, definite. So it's pretty easy, or at least positives. Yeah. And so then we can essentially get our lower bound. Does that all make sense? And from here, we can basically come back to what we had originally for our projection matrix. And we have an upper bound that kind of comes out from this. And if you basically, since it's diagonalizing this basis, this is basically the same as what we had asked for originally back here. Like that's the equivalent statement. And so on the lower bound, we end up with another term. And this is also a good spot to sort of highlight why the data splitting is so helpful. So here, basically, you're going to have a sum over, like, basically, you can think of it as an extra, like, division by n, or in this case, division by, like, capital N squared. But you're only summing over n terms. So you end up actually, like, making this term higher order and sort of vanishing, which obviously helps the analysis quite significantly. And so that's sort of how we get the balance in that object. And then we can also get, we can tighten these bounds quite a bit by essentially what we do is repeat the process on some of these intermediate terms. So if we go back up here, like we have a lot of these intermediate trace terms that we can repeat sort of the same notion on to get some tighter bounds that, again, like you can see, basically we have these division by n for the data splitting. We can basically significantly contract a lot of these things to just make these terms here. So that's sort of the key idea for the handling these A matrices. And that was sort of what I wanted to focus on. I think it was a little quick, but the key things that I think the future directions are sort of proving that, and the inflation property holds for like non-Gaussian covariates. Like what someone alluded to about, theoretical justification on when does the inflation property beat negative ridge regression, or does it always, or when does it? And then sort of what other interpolators or estimators for beta would this hold for? And so I guess I'll take some questions.
First, let's thank the speaker. Any questions?
Can you prove concentration instead of expectation for that trace A minus K?
You can do some probability bounds, but in general, there's not an easy way to just get so like what people often would think like, oh, we could do like a Wishart or look at some of the concentration results from Wishart matrices, but basically because of these lambda i's, you really can't use some of the concentration that we have there. And I guess I should have mentioned it earlier, but like one of the key differentiations between sort of this high dimensional work where like n over d goes to infinity compared to a standard work where sort of n and d are proportional is that you can't use the Marchenko-Pasteur law. So you lose a lot of like the concentration inequalities that people sort of take for granted in that regime. So
I'm a bit confused. If I take trace of I guess minus K is the issue, right? If
yeah,
I look at trace of A, it's a classical of sub exponential random variables.
Yeah, the issue is the inverse, is what it makes it much harder to handle these things. So you can show some things like you can do like, you can get concentration from like showing the variances, like, standard inequalities like that.
I do Sherman-Morrison and do some concentration with that. Because the Sherman-Morrison allows you to write it in terms of some quadratic form, right? In terms of, so you write A inverse and you leave one form out. So there are some, yeah. I just wonder whether you can do concentration instead of just expectation.
Yeah, so I guess like if you're talking about just like improbability, like you can show like I think I showed like,
because I think when you do Sherman-Morrison, there's a quadratic form out there.
Yeah, yes, there is. The problem with that is
that could give you something.
Yeah, the problem with that is that if you think about doing it like an iterative process of doing those quadratic forms over, is like it blows up around when d is around n. So you can't really easily like extract like the full A inverse object by doing that. But